Thank you very much for the introduction, and I'd like to thank the organizers for the invitation and possibility to present my work here. So I will, if I were to resume the content of the work in a few lines, well, it's basically about developing the infinite dimensional analog of the steepest descent method, which allows you to deal with one-dimensional or finite dimensional complex valued integrals. And the talk is based on a joint work with Alice Guillonnet and Alexander Little. So I would like to start the talk by motivating why one should be interested at all in such problems and in which class of problems those questions fit in. Then I would describe briefly the history of the topic, which will allow me to introduce some of the building blocks of the answers, which is necessary to understand what one gets in the complex valued setting. And then, according to time, I will try to give you at least some hints of the most crucial elements of the analysis which arise in the complex valued setting. So the first observation one can make is that integral representations are extremely convenient tools. They allow you to represent solutions to an outstanding number of problems arising through all fields of mathematics. Think about various examples of partial differential equations where you can provide integral representations for the solutions. Think about problems in enumeration theory, in particular analytic combinatorics, where you're able to resolve complicated sums of, say, combinatorial coefficients in terms of single or finite dimensional integrals, but also think about expressions giving you shapes or limiting or which allow you to access to certain limiting shapes of certain phenomena in probabilistic models such as Young tableaus, and more generally various probabilities of events in some probabilistic models can be described in a very convenient way through integral representations. And of course, there are special functions. There is a strong of integral representations allowing you to represent various kinds thereof. So after messaging out the formula, typically what one gets with an integral representation is a kind of a formula of the form. One has a certain contour gamma, which is piecewise smooth and bounded. It can be typically in the complex plane. You take an n-fold Cartesian product of those contours and you integrate e to the minus x. X is some positive real variable, times the function f of the n integration variables z1, zn versus the nth power of the line element measure on gamma. F is typically a continuous function or can have more regularities, and it grows sufficiently fast, at least in its real part, along the contour so as to make the integral convergent. And in all these examples, typically what one is interested in to having a certain limiting behavior of your solution represented by the integral representation. So you want to take the large, you want to be able to extract the large x limit of those integrals. So let us look first what can be done in the most classical setting of the Laplace method. In that case, one integrates just, it's a real valued setting, one integrates over r to the n. The function f is typically smooth, goes very fast to infinity, and then the ingredients of the method of analysis are the following. One looks for critical points of the function f, such that well, in the simplest possible setting, you have a positive defined Hessian at that point, and then what one can show is that the integral is dominated by the minimum of the function f on Rn, and the log of the integral goes linearly with x, with the value of f at the critical point, up to corrections, and the corrections can be computed order by a local analysis at ZC. Basically, you can bring the problem to Gaussian integration thanks to the Morse lemma, which locally rectifies your function into a Gaussian. Now, there is a second class of integrals one can consider, where one allows for complex valuedness of the functions and of the contour. So I'll just stick into the one-dimensional case because it's the most simple to discuss, and it It can already exemplify all the most important features. So in that case, we integrate over a certain curve gamma, unbounded, a function e to the minus x f of z. F is a certain holomorphic function from some open set UF, which contains gamma, into C. Its real part grows fast enough along gamma. So again, one wants to extract the x to infinity behavior of those integrals. And in that case, there are two ingredients. So first of all, one looks for critical points of the function f. But now, one does not look just on the contour gamma, one starts with, but on the whole domain where the function f is holomorphic. So this means that actually to the leading behavior of the integral, the main contribution typically comes not from the starting contour and one starts with, but from some locus of points which are far away from the contour. But this is not enough to find the critical point. One also has to find a critical curve gamma c, which is in the domain U where f is holomorphic, and which passes through the critical point, and which has the following property. The imaginary part of f is kept constant along the curve, and the real part of f has the fastest possible growth along this curve gamma c when one moves away from zc. And the reason for this is that these are typically oscillating integrals, because the imaginary part of f oscillates extremely fast due to the x prefactor. And what can happen is that even if you take a priori minimize over the original contour the real part of f, the oscillations can produce a completely different behavior in x. Once one, and then the point is that because one is in a holomorphic setting, one can start from this integral, then deform using Cauchy theorem the original integration curve to gamma c, and then carry out the analysis basically as in the previous case. Again, the integral is dominated by a vicinity of zc and a local analysis. So you start with a linear connection in x in typical settings, and then corrections are computable order by a local analysis. So this is so far I have the and you can up to some hypothesis and in some setting you can extend this line of thoughts to finite dimensional integration over curves in the complex plane. So far I was discussing how the setting of classical integrals, which is extremely well understood today. So it is the setting where the parameter x goes to infinity and the dimension is fixed. But there is an increasing number of examples of integrals when one would be interested in extracting the asymptotic behavior of n-fold integrals in the limit when the number of integration grows. And well, one example is partition functions of statistical mechanical systems. So typically here I give one example. In one dimension, you have n particles z1 with position z1, zn, which live on R, each living on R. They are confined by an overall potential V, which produces this term in the multiple integral, and they may integrate through all between themselves through a two-body interaction omega of a certain form. So there is a parameter here in front, 1 over t, called the temperature, and typically one is interested in the behavior of such partition functions in the thermodynamic limit, so when the number of particles goes to infinity, when the parameter t is positive. But in fact, they are, over the years of investigating such systems, it turned out that there are interesting properties of such partition functions also when one allows the parameter t to be in the complex plane, and in particular, the zeros of those partition functions when n is very, very large, the so-called Fisher zeros. So those integrals, they are real-valued in certain cases, and they may also have complex-valued integrals. More generally, if one would like to construct a quantum field theory in the Minkowskian setting, one can do it by a sort of discretization of the hypothetical path integral, which by considering integrals of such a form. So again, one integrates over Rn, some function v depending typically on n, which only involves one integration variables, and a function wn, which involves two neighboring variables or more, which depends on n, and takes the products over all variables up to periodic boundary conditions. And this is typically a complex valued integral. Also, there are many examples of structured determinants which arise in mathematical physics, in particular Toplet's determinants, as I write here, and one is interested in the large n behavior of those determinants. So here, a Toplet's determinant is a determinant of a matrix which is built from Fourier coefficient k minus L in A3 KL of a function, say, e to the minus nv, n being the size of the n by n matrix. Here one computes this, and one wants to study the large n behavior of such determinants. For instance, they arise in the study of the two-dimensional correlation functions of the two-dimensional Ising model. And after some elementary algebra, one can write it out as the following n-fold integral. So in some cases, you have, and you will typically have complex valued potentials V. Finally, and this is maybe the main motivation from my point of view why to attack the problem, is trying to make some sense of the conjectured representations for the so-called correlation functions of quantum integrable models, whatever this would mean, but you can really interpret them from the perspective of special functions theory as the special functions which lie just above the Paul-Levé class, just as Paul-Levé transcendence, generalized transcendental functions such as the hypergeometric functions. So these functions are constructed typically as a series of integrals whose dimension an grows to infinity with n. And you integrate over a certain curve C in the complex plane with an integrand, which depends on some parameters xt, the parameters of the function, and which has a rather involved form, which I will not give you here, and it's typically complex valued. And you would, so the main problem with those representations is that you don't know whether the series actually make sense, and for that, you need to check how you need to have tools to know how the integral defining the n summand of the series grow with n. So you need to be able to do such dimensional asymptotics. So let us, so basically to resume, the next setting is to consider integrals over certain contours gamma to power n in the complex plane, where you integrate functions fn, which are well behaved or not so badly behaved, and where you take them in the exponent and you have some prefactor xn which goes to infinity with some speed in n, and you want to extract the large n behavior out of such integrals. So, so before going to the setting we were considering, which is the complex valued, which is trying to study the large n behavior of certain examples of such integrals with complex valued functions fn and contours in the complex plane, I need to do a detour and describe you what was already well known in the case of real valued integrations. Because this will also allow me to introduce various tools which will arise in the description of the complex valued case. So one example of such integrals, which enters in the realm of, which are usually called beta ensembles, takes its roots in the theory of Hermitian matrices M. So pick a matrix M, which is a Hermitian matrix, which is distributed with a measure which is continuous in respect to the Lebesgue measure on the independent entries of M, with a density which is given e to the minus 2n, the size of the matrix, times trace of V of M, where V is a continuous function going sufficiently fast to infinity at infinity, and normalize all this so that it's a probability measure. So Hermitian matrices will have typically eigenvalues lambda, will have real eigenvalues lambda 1, lambda n, which are typically of multiplicity 1. And so you can express, you may want to express this measure in the coordinates which diagonalize your Hermitian matrix, so the unitary matrix doing the diagonalization and the diagonal part parameterized by the eigenvalue. You can compute the Jacobian of this change of variables, and what you get is that the probability measure, when starts here, factorizes into a Haar measure on the unitary group times Lebesgue measure on the eigenvalues times the density e to the minus n square times an explicit function h, all this normalized by the so-called partition function, depending on the potential Vi starts with, so that one gets a probability measure. And Hn, you can think of them as the spectral density. It takes the explicit form, so you have the contribution of the potential part, and then contribution of the change of variable Jacobian, which is a logarithmic integration between the integration variable lambda n. And the partition function is such that the spectral part of the measure is normalized to 1, so it takes the following, the form of the following n-fold integral. You have a van der Monte square of the integration variable lambda and e to the minus 2n v of lambda a product over n. And in fact, well, you can generalize these integrals by adding a parameter beta here instead of having exponent 2 and a parameter beta here. Beta equals 1 and 2 correspond to other ensembles of random matrices, but you can also consider those integrals in the general setting. And then you see you have a sort of singular interactions, two-body interaction and a regular one-body interaction. Now, what are the main steps to extracting the Largen asymptotics of the partition function? So the first step is to argue that actually the partition function on when you integrate over Rn is the same as the partition function when you integrate over k to the n, where k is sufficiently large compact in R. This up to exponentially small corrections. And then what you try to do for this kind of partition function on a compact associated with a compact set, you try to estimate the growth of the integrand. And so there's a nice way of rewriting the two-body, the integrand in terms of e to the minus n squared beta over 2 times a certain functional, epsilon, which acts on a so-called empirical measure. So it's a probability measure on R, where you sum over the Dirac masses evaluated at integration variables lambda 1 to lambda n, and you weight it by 1 over n, so that you have a probability measure, and that's you can do when the lambdas are away from the diagonal of k to the n. And what you get here, epsilon, is a regularized energy functional, so it's given by a quadratic functional in the measure which is evaluated. You sum v of s plus v of t, and then you remove the diagonal for the logarithmic interaction so that this evaluation makes sense away from the diagonal of k to the n. And now let me just heuristically show you what one gets in that case. So one integrates over this set Kn when one removed the diagonal. Now the integrand is rewritten in this fashion, and you have the Lebesgue measure. So the Lebesgue measure, because you are on a compact set, will typically, at most, it will produce the volume of k to the n, volume of k raised to power n contributions. So then, if you just follow the analogy of the classical Laplace method, the integral should localize in the minimum of this functional. And then because you move integration variables throughout a very large set in k to the n, you may expect that this ln will actually scan, when n is very, very large, through all sets of probability measures. So you expect that this integral will be roughly given by minus n squared beta over 2, just the prefactor here, times the minimizer of this of the functional appearing here, now over the space of all probability measures on R. So you also expect that, well, there was kind of regularization here when you remove the diagonal, and you expect that, well, this should not matter so much in the Largen limit, so you should just consider the functional where you don't need to regularize the diagonal, and then you may have some smaller order contributions of magnitude to be determined. All of this can be, and now the second point is that actually by doing some potential theory, you can prove that this minimizer of this energy functional is attained at a unique probability measure mu ec, which has actually some nice properties if you put some a few properties on the potential V. Now, all of this can be made fully rigorous within the framework of large deviation theory and concentration of measure. And what you get in the end is that the log of the partition function goes like minus beta over 2 n squared times the evaluation of the energy functional on its minimizer up to corrections. And in particular, this was pioneered by in these works. Now, to get the subleading corrections, the good way to grasp it is through by studying the convergence of linear statistics. So what are those? You take this empirical measure I introduced you before. So it's and you integrate it versus some test function f sufficiently regular. And this empirical measure would be a random measure distributed with the probability measure associated to the partition function. And you would study expectations under this probability measure of products of such linear statistics. What you can show, and this was pioneered by these people inspired by Schwinger-Dyson equations arising in quantum field theory, is that those expectations satisfy an infinite coupled systems of equations which couple expectations in one linear statistics with those in two linear statistics and etc. So in itself, the system is not closed because it's infinitely coupled, but if you go to the large n limit and you observe that you have a certain concentration of measure in the sense that the linear statistics and analogously products of linear statistics concentrate on around the equilibrium measure, which was the minimizer of the energy functional I showed you before, with some a priori bounds of square root of log n over n order, then the Schwinger-Dyson equation actually triangularize in the large n limit. You can solve them, and by this you can show the existence of all other asymptotic expansions, in particular for one linear statistics expectations. And you can compute these terms in the asymptotics by order calculation. So, and then to get to the partition function, what you do, you use interpolation. So the important point is that if you consider Gaussian potential in the beta ensemble case, then the partition function is nothing else but is given by a Selberg integral, for which you have a closed formula. And you can analyze it in the large n limit. So then, the log of the partition function of interest, at least in certain cases, you can write it out as an integral from 0 to 1 of certain expectations of linear statistics of a function which is related to an interpolation of the potential V between your potential of interest and the Gaussian potential. And if you control this all order asymptotics sufficiently well in V, so that you have a uniform asymptotics in T here, you can plug in the asymptotics, integrate, and get to the result. So let me present the result, and then I will be able to make the analogy with the complex case. So if you consider potentials V which are regular enough, which grow faster than logarithmically at infinity, and you focus on a particular case of an equilibrium measure mu f, which is supported on a single segment AB, which is off-critical, which means that its density, it has density in respect to the Lebesgue measure, which has square root behavior at the endpoints of its support, and is multiplied by a function h, which is strictly positive on the support. Then, what you can prove is the following large n expansion of the partition function in the following form. The expansion starts with an n squared term. Then you have a leading term, which is what I already showed you, an energy functional, the value of the estimation of the energy function on its minimizer. Then you have n log n term, which are potential independent and just come from the Selberg integral part, so the partition function of the Gaussian potential. Then you have a linear term in n, which is nothing else but the entropy of the relative entropy of the equilibrium measure in respect to the Lebesgue measure, plus the constant, which is V independent, so fixed by the Selberg integral part. Then you have a logarithmic term, again, V independent, so stemming from the Selberg integral, and then you have a 1 over n expansions with some coefficients which you can compute to arbitrary precision by order calculations. So those results, they were obtained by Albeviro, Pasteur, Sherbina, then Ercolani, McLaughlin for specific values of beta, and then in the general setting by Bourreau and Guillonnet. And actually, the analysis extends to more generic cases. In particular, you can deal with generic potentials V, in which case today it's rigorously established that the equilibrium measure in that case will have the support will be given by a union of segments. And also you can deal with much more complex integrals than those I've shown you before, and in particular it was developed by these people and probably in other works as well. So if I miss somebody, I'm sorry. But the main caveat of the method is that this line of reasoning breaks if you step out of the real valued setting. So the goal of the work was to push this kind of ideas and develop techniques to deal with the complex valued setting. So let me first start by presenting you the main results, and to do that, I first need to show you what was the object we started with. So the object was very analogous to the one I showed you before. We consider a beta ensemble integral where we have a Vandermonde raised to the power beta. We have a confining potential V, exactly of the form as I shown you before, but we integrate over a curve gamma in the complex plane versus the product of the line elements on gamma. And we want to have a holomorphic setting. So first of all, we want to integrate holomorphic functions. So for that, we cannot take arbitrary beta. We need to take beta an integer. And because of trivial permutation antisymmetry, the partition function is 0 and beta is odd, so we consider beta even. Further, we focus on the simplest possible case of potential in order to simplify certain technicalities, and we just consider complex polynomials, V. And because of scaling invariance of the integral, you can just focus on polynomials which have those kinds of leading coefficients, 1 over kappa, z to the kappa, plus subleading terms. Kappa is an integer. So now, those potentials, what you see is that they have regions in the complex plane where they grow very fast, and the real part goes either to plus infinity or minus infinity. In particular, you will have rays in the complex plane where, where the potential given by the directions 2I pi over kappa times an integer between 0 and kappa minus 1, where when one moves along this ray, the potential is equivalent just to its real valued along this ray, and it grows like 1 over kappa t to the kappa. So those are the good rays for having strongly convergent integrals, and one has to avoid rays where you have where the potential is equivalent to minus its real part, which would kind of be between those regions. So having identified the growth rate of the potential, we have to specify on which curves we want to integrate. So we want to integrate over curves, which will be continuous in the complex plane, and which would be such that when you move away from a disk sufficiently large, then the curve would coincide with one of the rays of fastest growth of real parts to plus infinity of the potential. And because of Cauchy theorem, you want to focus on curves which connect two different regions of growth. So for instance, curves which would grow like this and then like this. Because if you would just do a certain loop somewhere here and move along one direction, you can just contract the integration curve to 0 using Cauchy theorem, and you get 0. But here, because you have lines of infinite growth, you cannot do it anymore. So just as in the real valued beta case, you had a certain energy functional which was controlling you the leading asymptotics. In this complex valued case, you have an analog of that, which is the real energy. So it's given by the log. So it's given the real energy, which is associated to a curve gamma, the type I've described, is a quadratic functional on the space of probability measures on gamma. You would integrate the product of two measures, d mu of z, d mu of w, versus log of 1 over absolute value z minus w, and then you would add the real part of the potential v in z variable, real part of potential v in the w variable. So you can use potential theory exactly as in the real case to show that you have a unique minimizer on the space of probability measures on gamma of this real energy functional, mu gamma, which has several nice properties which I don't list, provided you take in our polynomial setting. But now there is this second add-on of the complex valued setting, which is the maximum energy problem, which was considered in the first time by Kambrisis and Rachmaninoff in 2005. And it deals with the following question. So you have a fixed curve gamma, you can study the minimizer of E gamma, but now, can you find the largest possible minimizer of E gamma when you allow the curve gamma to vary in an appropriate class? And this is the class of curve to which I restrict. So curves which go to infinity along two chosen rays of fastest growth of f, and which can move as you want in between. So you consider the problem of minimizing first the real energy functional on a curve E tilde gamma over the space of probability measures on that curve, and then you take the supremum of all curves gamma tilde in the class I described. Well, because of potential theory, the unique minimizer exists, so you just take the supremum over the curves gamma tilde of the evaluation of the real energy on its minimizer on gamma tilde. And then for complex potentials V, and actually classes of curves even more general than those I've shown you before, Cuixlas and Da Silva managed to show the existence of a solution to this problem. So what does it mean? It means that you can find equilibrium curve gamma egg, it's not unique, and you can find this time a unique probability mu on gamma egg, and it's unique independently of the certain freedom of choice of gamma egg, on which I will comment later on, such that this soup of this maximum energy problem is attained on the curve gamma egg and on the curve mu egg. So what is important here is that what is fixed in gamma egg is the support of the equilibrium measure and the equilibrium measure itself. Because you can imagine that maybe the curve gamma egg, the support of this equilibrium measure would be just this piece of the curve gamma. But then, because the functional only evaluates on the equilibrium measure, so all shapes of the curve gamma egg away from the support do not matter in the value of the equilibrium measure. So what happens away from the equilibrium, the support of the equilibrium measure is not uniquely fixed, but the part of the equilibrium curve on the support of the equilibrium measure mu gamma egg is fully fixed. Moreover, this equilibrium measure has very nice properties. It is absolutely continuous in respect to the line element measure on the curve gamma egg. The curve gamma egg is an analytic curve, so as regular as you want. And the equilibrium measure is the square root of a polynomial R of z. And the support of the equilibrium measure is given by a union of segments AS, BS. And by segments, I mean, segments inside of the curve gamma. Okay, so now I have enough, introduced enough notation.
all of the maximizer
Mhm.
restrict the curve to support the
Yes.
but it's always the same.
Yes, yes, yes. So the part which gives you the value of the minimizer will be fully fixed. Yes. So away from the support, you can well here you are not in a holomorphic setting, so you integrate real part of holomorphic functions. So this is fixed, but anyway you this curve. So suppose you have a equilibrium measure which has sort of two cuts, then the red curve and the shaded curve do the job as well. For this problem, it's just the real part of a holomorphic function, but the whole is a holomorphic setting. But you use max mean problem for a sort of real part of something holomorphic to set up the asymptotics. Yes, yes, yes. So that the potential V grows the fastest possible along the curve. And now, so among all this structure of curves, we can specify to one setting, which is analogous to the setting I've described you for beta ensemble, which is one cut. So we just focus on the case of an equilibrium measure, which is support on one arc of the equilibrium curve gamma egg. So like one segment, and which is off critical. So it means that it has square root singularity. So it's absolutely continuous in respect to the line element on the curve gamma egg. It has square root singularities at the endpoints of the curve segment AB. And it's multiplied by a function h, which is non-zero on the whole curve gamma egg. Yes, it's actually this h of z is polynomial. Because we are in the polynomial setting. And then the large n behavior of the log of the partition functions takes the following form. So it's very analogous to the beta ensemble case. You have an n squared term with a explicit coefficient, which I will describe, and log n term, which just comes from the Zelberg integral part, then linear in n term, which I will explicitate also, log term coming from the Zelberg part, and a large n 1 over n expansion with coefficients computable order by order, and the asymptotic expansion holds for all cases. So the leading term is given by a complex energy function. So it's the evaluation of a complex energy functional associated to the curve gamma egg, which solves the max mean energy problem, and evaluated on the equilibrium measure associated with this curve gamma egg of the real energy functional. And what is the complex energy functional? Well, it's just sort of the complex analog of the real energy functional. So it's a quadratic functional on the space of probability measures on gamma. You integrate v of z plus v of w, and then you integrate log of z minus w. But log of z minus w, it's a function which has cuts. You have to be very careful which cuts you choose. I don't want to go more deeper into those technicalities. You choose the cuts of the log so that it roughly has, so it has cuts along the curve gamma, and you sum the plus boundary value of the log and the minus boundary value of the log on this curve gamma. And I will comment on how this is related to the previous problem later on. And then you have first subleading corrections, and this is just given by the complexification, again, of the answer you get for the real beta ensemble case. So it's the relative entropy, now it's complex valued, of the equilibrium measure in respect to the line element on the curve gamma egg with the same constant as you get in the beta ensemble case. Yeah, and it's complex valued because even though mu x taken as a full is a probability measure, but the line element has some complex valued parts. So if you just take the density here in the log, you get something genuinely complex valued. So let me comment a little bit on the results. So first of all, this kind of problem was considered before in the Riemann-Hilbert community by studying the systems of orthogonal polynomials associated with such partition functions through the solution of matrix Riemann-Hilbert problem. And this allows you to access to the larger asymptotics. But those techniques are only applicable to beta equals 2, because then it's only then when you have a connection with orthogonal polynomials and beta ensemble partition functions, and they only treated the case of polynomials of the degree 3 and 4, and this was done by those people. Now, as I've told you, the leading asymptotics in our case are graphed by the complex energy functionals, and they are related to the real energy functionals which arise in the max-min problem, just by taking the real value of, if you take the complex potential, complex energy functional associated with the curve gamma, evaluated on the probability measure on gamma, you take its real part, you get the real potential. Now, what are the possible generalizations of the results? First of all, once the main kind of frame has been developed for the one case, it's not a problem to apply the techniques which were already fruitful for the revalued beta ensemble to deal with off-critical multi-cut case, which again should be generic case of generic potentials V. And it will be also okay to deal with generally holomorphic potentials or maybe something like this, but then on technical grounds, the max-min energy problems will be more complicated because the description of the minimizing curves gamma x will be much more complicated for holomorphic V. Now, what I would like to convey to you now is, in the remaining time, is the main idea of the proof, and in particular, why the max-min problem arises at all in this kind of setting. So what you can do direct bounds. You start with your complex valued beta ensemble partition function, you take the absolute value, you move the absolute value in, and then you bound it by a real partition function. So it's what it is, it's just the beta ensemble-like integral where you have put absolute values of on the integration variables van der Mond raised to power beta, and you just keep the real part of the potential, and you integrate versus the absolute value of the line, nth power of the line element. And then you apply real variable techniques in the sense I described you before. You can very well study these kinds of partition functions. And what you get is that the limit actually of the 1 over n log of the real valued partition function is given by the infimum over the space of probability measures on gamma of the real energy functional, which I described before, which would be the natural energy functional for this integral, evaluated on mu. For any positive vectors. Next step, what you observe is that you have a certain contour deformation invariance. So because you are in a holomorphic setting for the complex valued beta ensemble integral, you can deform the contour gamma originally you start with to another contour gamma tilde, which is in the same class, so that it goes away along the same rays at infinity. So now you have a control by a real partition function. So you start with the partition function, complex valued partition function you were interested in. Then you deform the contour to some gamma tilde, and you control this partition function by the real partition function, but now associated with gamma tilde. Eventually, what you want is you want to know the large n behavior of this. So let us look at the upper bound of the large n behavior. Well, so you take 1 over n squared, the lim sup of the log of the partition function, complex valued, but absolute value of the complex partition function you wanted to have. So you take the log, you divide by n squared, take the lim sup of this partition function on now gamma tilde in gamma, so on a different contour. This exists by what I showed you before. And so it's well, it's, equal here to minus beta, the infimum over the real energy functional on gamma tilde. Now gamma tilde is a free parameter, so you can optimize the bound by taking the lowest possible bound, so by taking the supremum of this quantity over all curves in gamma tilde. And this is, at least heuristically, well, this is how you would get the upper bound. Where it's optimal or not is another question, because you need to know.
Now beta
Now beta is an integer. Yes. Yes. And so this is how you get one possible upper bound. You don't know if it's optimal or not, but at least you have some upper bound on the log of the absolute value of the partition function by the solution to this max mean energy problem. So real energy functional on the minimizing curve gamma ek and evaluated on the probability measure. Okay, and now to check that it's the bound you want, you need to do something about the lower bound. And in the lower bound, you already start to see a bit more structure on what the equilibrium curve is. So just as in the real valued case, what you can do some form of compactification of the integration curve. So, so basically you can reduce the integration curve up to exponentially small corrections, and one concerns the value of the partition function by, so what you would do, you would start from some solution to the max mean problem gamma ek, look at its associated real partition function z, and then, well, you can show that you can actually, what produces the leading contributions up to exponentially corrections is a restriction of gamma ek to a very small neighborhood of the support of the associated equilibrium measure. And you can have this, and you have the same for the complex valued partition function. And what you do, now you have to be a bit more careful about how you would choose gamma ek, because some choices are better than others. So as I said, you can choose in principle the maximizing curve gamma ek for the max mean problem in an arbitrary way away from sup gamma ek. And you would like to choose it in the most regular way. So what you can show is that there exists a parameterization gamma ek of this solution to the max mean problem, such that it will push forward your equilibrium measure to the semicircle law on 0, 1, and that gamma ek will be analytic in a small neighborhood of 0, 1. There is some canonical way to construct such parameterization gamma. And then what you consider is the probability measure on this small neighborhood of the support of the semicircle law, 0, 1, of this form. And this is just the probability measure you would get from the real partition function if you would change variables from the z variables to reparameterization of them by gamma ek. So you just set J is gamma ek of x. And you get this kind of probability measure on R. So then what you can do, you can re-express your complex valued partition function in terms of quantities related to this real partition function. So you consider this ratio, and then after some massaging of the formula, you see that the complex partition function is nothing up to a prefactor which is fully explicit. It's some quadratic functional in the semicircle law. You get an expectation in respect to the probability measure I've shown you before of the exponential of in times a certain explicit functional g ask of the Fourier transform of the recentering of the empirical measure on the semicircle law multiplied by normalized by n plus I times another quadratic functional in so this functional is linear in this Fourier transform, and then some functional which is quadratic in the Fourier transform. And now the point is, how do you see that the min-max problems kicks in into the game? So I will not give you the expression for this functional, but what you see is that if you take the solution gamma ek, mu ek, so if in here you consider the solution to the max-min problem, and you consider it locally analytic in the sense I've shown before, then this term is exactly zero. And this is exactly what is happening in the case of one-dimensional integrals, because what you do, how you choose the steepest descent curve, you choose it to kill all oscillations. And this is why this does the job. And then what remains to evaluate is this kind of expectation of a quadratic form in the phi n's. So this is already quite standard using probabilistic tools. The functional J in is an explicit quadratic functional in the phis. You have, for the measure I shown you, you can establish concentration of measure results. You can, which are very analogous to the reevaluate setting. You can set up a system of loop equations, which you can study in the large and limit, analogously to the reevaluate case. You get the existence of all other asymptotic expansions for the expectations of linear statistics and related quantities. And then you have convergence and distributions of the phi n's to Gaussian random variables with explicit mean, explicit covariance. So then from this you get convergence of the expectations in the large and limit, and what remains to do is to check that the limit is non-zero, so you have to evaluate the Gaussian expectation of the exponent of a quadratic form in the random fields phi. You can do it by Gaussian calculus. The explicit formula is not so important, but it's basically some quadratic exponent of a quadratic expression involving the mean, the integral operator associated with the covariance of the fields, and the operator A and the function P, which were arising in the expression of J in. The detailed expression is not important. It's just what is important is that it's well defined, non-zero. In the denominator, you have a square root of a certain Fredholm determinant. It's, again, everything is here well defined. And from that, you get, first of all, lower bound on your complex partition function by the real partition function. So you already know it's non-zero. This was not guaranteed a priori because of the presence of oscillations. And you get the first term of the asymptotic expansion, which is the evaluation of the complex energy functional associated with gamma ek on mu ek by just following back the calculations. And then to get the all order asymptotic expansion, well, again, there is a slight difference with beta ensembles. So in beta ensembles, what one was doing was one was taking a very naive interpolation, at least namely, one was considering potentials, linear interpolation between the potential of interest and the Gaussian potential, and then one was integrating the expectation value of probability measures associated with Vt of certain linear statistics associated with the interpolation potential. And this works actually very well because the equilibrium measure associated with potential Vt is a convex combination of the equilibrium measure associated with V and Vg if one uses Vg nicely in the case of the one in the case where the equilibrium measure has one segment support. But in the complex setting, if one would take such a convex combination of two potentials, nothing guarantees you that you get the same equilibrium curve for all values of t. Actually, you would not get it because you can compute the equilibrium curve for a Gaussian potential. It's just a straight line. And as soon as you have polynomials of degree higher than 2, then it will be curves in the complex plane. So if you would like to find some way to interpolate like a convex combination of one solution of min-max problem and another one, it would just not make sense in the immediate calculation. So what you need to do, you need to find another way to interpolate. You need to find a sufficiently nice holomorphic potential V, and this time it will not be polynomial, which will help you to interpolate between the Gaussian potential, for which you can compute the curve, and the polynomial potential for which you want to compute the curve. And you will use this interpolation not on the full curve, where it would be extremely hard to control the asymptotics of the interpolating holomorphic function, but just on a small neighborhood of the support of the equilibrium measure, which allows one to do such a construction. I will not go into the detail of this. And once you have this interpolation potential, then you can just proceed as in the real beta ensemble case, where this time you will consider expectation values of linear statistics of certain t derivatives of this interpolating potential V, but in respect to a complex valued measure, which now you control very well because you control the leading asymptotics of your complex valued partition function, and these expectations satisfy a similar system of loop equations, which you can analyze. You have all uniformity in T. You want to do the integration order by order in N, and you get the result I showed before. So what I've shown you is that it's possible now to set up an infinite dimensional analog of the steepest descent method for complex valued integrals, and we managed to set it up in the framework of complex valued beta ensemble integrals when we considered polynomial confining potential and one-cut equilibrium measure, which are off-critical. So as I said, it's doable. The method is definitely extendable to the multi-cut off-critical case for polynomial potential, and if you increase a bit the technical details, then it's definitely also possible to deal with holomorphic potential. And then for further development, it would be extremely interesting, at least for me, to be able to apply this kind of methods to the integrals which arise in quantum integrable models, like those defining these correlation functions of quantum integrable models, so as to make those expressions rigorous. Thank you for your attention.
Thank Professor Kozlowski for this very illuminating talk. Any questions?
Thanks for your talk. So maybe this is in the last bullet point here, but do you have any thoughts about what might happen if you wanted to do, n-fold contour integration where the gamma is different for each integration variable? Maybe you have a potential z to the n, and the n, little n and big N are proportional, and so you have lots of different possible contours.
No. Maybe in that case, what one should do, but this would depend on the integrated problem, is to try first to symmetrize the integrand to integrate everything over a symmetric contour. This would change the form of the integrand also, and then try to attack the problem in this way. But this would really depend on the precise setting.
Great. Thank you very much.
What do you mean by more complex integrals?
Well, more complex would be, instead of considering just van der Monde to power beta interaction in a one-body confining potential, consider integrands which are much more coupled and which introduce much more couplings between the integration variables. Yes, so you for instance, you would introduce three-body interactions, four-body interactions, but also in a less explicit way than just in terms of products.
If I understood correctly from your talk, you fix asymptotic directions where your eigenvalues going, right?
Mm-hmm.
But on the other hand, as also, if I understand correctly, analysis depend only on this finite support eventually for asymptotic expansion. Can I just then curve the line to go to other?
So
and
yes,
it doesn't change the result then.
Actually, it would. For instance, you could imagine integrations on more complicated domains. So we consider just this domain because it has less silly behaviors for the support of the equilibrium measure. But you could For instance, consider just as well, for instance, a curve which would go something like this. So you would have like three legs. The integral is perfectly defined because it's all convergent direction. But then in that case, the support of the equilibrium measure can be more, could be in principle more complicated because you could have meetings of this sort, and then one would have to deal a bit more precisely with
Okay,
it.
so the support of the measure actually depends on the boundaries you choose.
It depends on the number of legs the contours have where they go to infinity and how they connect the legs. You would have a whole classification of directions going to infinity, connected or disconnected, and this would fix the support of the equilibrium measure.
Okay, so let's thank Professor Kozlowski again.